We're saying this is a mathematical modeling in biology course. We're going to talk about the main ideas for modeling problems in biology using mathematical systems or mathematical tools. And the main idea is the use of dynamical systems. Okay, and the basic idea of of dynamical systems is to model concentrations, populations, etc. over time, okay, using a differential equation ordinary differential equation or ODE. Okay, so the most simple ODE I can think of is the model of population growth. So suppose that n of t is the population of bacteria over time. So you grab a bottle of bacteria, actually a bottle of sugar, and you put a bunch of bacteria in it, and you let the whole thing evolve over time. So here's a bottle. Let's say that you start with just one bacterium, and after a while you wait, and you get 2 bacteria. Okay? Now, let's say that this time was, I don't know, 2 hours. So what happens after 2 hours? You get 3? Or how many? 4, right? Okay, fine. So you get 4 bacteria after the same amount of time. And the same thing over and over. So this growth is what we call exponential, right? How do we capture this thing mathematically? Well, one thing we could do is, and this is what's done in a whole course last quarter, is to assume that the number of bacteria is discrete. And that there's also discrete amounts of time, after one amount of time, after 2, 3, and 4. Now we're going to go one step beyond that. We're going to assume that the time is continuous. So time now is a continuous variable, and the population is also a continuous variable. Mind you, that's already a simplification. We're assuming that the number of bacteria is a continuous variable. There's actually no such thing as 10.5 bacteria, right? You cannot talk about 10.5 bacteria. But we're assuming that the number of bacteria is a continuous number. Why do we do that? Why do you think we can get away with that? It sounds kind of a weird thing to assume that you can have 10.5 bacteria, right? Well, we do that because otherwise we cannot write a differential equation. Differential equations usually involve continuous variables. First reason. Second reason is that the number of bacteria is usually so high, we're not talking 10 bacteria, we're talking 1 million bacteria, that it doesn't really matter, right? So we're going to assume that the population is continuous and time is continuous as well. So assume that n and time are real numbers. Okay, so now the differential equation I have in mind for this, maybe somebody can offer what would be the simplest equation for this system. What do you guys think? dn dt equals lambda n, or constant times n. We're going to call this constant k times n. Okay, what does this mean? Well, the rate of growth of bacteria is on the left-hand side, and on the right-hand side we're saying constant times n. So in particular, this means that if you start with, let's say that you have a bottle with 1,000 bacteria over here, and over here you have a bottle with 2,000 bacteria. So which of the two populations grows faster? Of course, this one right here, right? According to that equation, how much faster does this population grow? The one with 2,000 bacteria. 2 times faster, right? So if you start with 1,000 bacteria, you grow half as fast as if you start with 2,000 bacteria. That is really what the equation says. It doesn't say anything other than that. It says that the rate of growth is proportional to the population. Okay? That is this idea that if you start with 2 bacteria, you grow twice as fast than if you start with 1. It's basically encoding this idea that the bacteria don't care how many other bacteria are around, as long as each of them has enough sugar to grow, they grow at the same rate on their own, depending on how many other bacteria are in the same bottle. Okay? So that already is a big modeling assumption, and it's all encoded in this equation. This is what we call an ordinary differential equation. I know you guys probably all know this, but let me just state it in case you didn't. This is a differential equation. It's an equation where the unknown is a function. Is a function n of t satisfying in this case n prime equals k times n. Okay, so does anybody want to venture a function that satisfies this equation? Pretty easy actually, right? So what do you think? Or what do you think? That's right, n of t equals e to the k times n? Times t, right? Times t. Okay, so let's check that this function satisfies this equation. How do we do that? We just plug it in, right? Okay, so n prime of t is equal to e to the kt times k, using the chain rule, right? And because e to the kt is n, this is equal to n times k, which is just k times n. Okay? What would be, is this the only equation, the only function that satisfies that equation, or is there any other one? What do you think?
Sine of kt?
No, I don't think sine of kt works. Because the derivative is cosine, right? Yeah. Yes?
Constant times e to the kt?
Yeah, exactly. You can actually multiply this by a constant, right? So let's do this real quick. If n of t is a times e to the kt, then n prime of t is equal to a times e to the kt times the derivative, which is k. Okay, and this is n, of course, then this is equal to k times n of t. Okay, so it also satisfies the ODE. In practice, there's actually a whole family of solutions. One solution for each constant. Okay, and you can also prove, but that's actually harder to prove, that every solution of the ODE is of this form. Okay, that's not so easy. We actually have not done that. We just proved that there's a whole family of solutions that satisfy the equation, but we didn't prove that all solutions look like this. But you can also prove that. Okay, so the solutions of the ODE n prime equals k times n can be written as n of t equals a times e to the kt for a constant. Okay. Now usually we provide what's called an initial condition. Okay? The initial condition is the original population, with the population at time 0 or the population at time 10 or whatever. So for example, n of 0 equals to 100, we call this the initial condition. And the initial condition can be used to figure out the constant A. Okay? So if we're given n of 0 is equal to 100, then how can we figure out A? Well, we just plug it in, right? So n of 0 is equal to A times e to the k times 0, which is equal to A times 1. On the other hand, n of 0 is equal to 100. Okay? That means that A is equal to 100. And that n of t is equal to 100 e to the kt. Okay. I know for many of you guys this is all very basic, although let me make sure that you guys are on second year, third year? Third year? Okay, who's in second year? Second year is sophomore, right? Sophomore? No sophomores? Okay, what about juniors? Okay, what about seniors? What about retired people? One, okay. All right, okay, good. So, all right, fine. Because, you know, this course really has very basic prerequisites. So I want to make sure that people who are taking this course but did not take any more advanced course like Math 13 or something like that are gonna, you know, are missing out. So I want to make sure this is very basic stuff, but I wanted to say it, okay? We're gonna make this a little more complicated now and assume the following. Actually, before I do that, let me ask you, what about the half-life? I'm sorry, not the half-life, the doubling time of the bacteria. If I have an equation like that, how do I know how long it takes for the bacteria to double in population? Yes, double the initial condition and find t. So let me write that here. So doubling time so this is the time that it takes for the bacteria to double, of course. So suppose that n of t0 is equal to 2 times n of 0. Okay, we want to find t0 such that this condition is satisfied. Well, we know the equation for n of t, right? N of t is equal to a times e to the k t, in this case kt0, is equal to 2 times a times e to the k times 0. So that means that I can cancel out the a on both sides, and this of course is equal to 1, and I get e to the k t0 is equal to 2. Okay, and I would like to solve for t0, so I'm going to take the logarithm on both sides, and I get I take the logarithm on both sides, so on this side I get k times t0 is log 2, and that means that t0 is equal to log 2 over k. Okay, now back to the modeling. Remember, we're now thinking about modeling problems. So the t0 has units of time, right? Minutes, hours, whatever. So what would be the unit for k? Did you ever think about the units for this constant? It's 1 over seconds or 1 over minutes or whatever. So that means that the units for k are 1 over time. Okay? It's an interesting thing. What are the units for n? Now that we're talking about units. What do you think? N is the population, right?
Bacteria.
Exactly. Could be the number of bacteria. Believe it or not, that's a unit. It's kind of a weird unit, right? We're not used to thinking about number as a unit. But if you've taken a chemistry course, when you think about mole, a mole is a number of molecules, right? A mole is equal to, I don't know, 10 to the 6 point something times 10 to the 24 molecules, right? So it's actually the same thing as bacteria. It's just that it's a larger number. We can come up with a mole for bacteria, but who cares, right? We just call it number of bacteria, that's it. Or sometimes we're going to think about the density of bacteria. So it could be, for example, the number of bacteria divided by volume. For example, number divided by centimeter cubed. Okay? All right. So now let's make this a little more interesting. What if we have this constant k depend on other things? So again, let's think as modeling people. What assumptions are we making in this model? What do you think is something that is not necessarily satisfied in this model in real life? For example, is it necessarily true that the bacteria can have as much sugar as they want to survive? Or as much space? No, right? Sometimes they may not have enough sugar to grow. In which case, what do?
Not grow.
They don't grow, or they don't grow as fast, or they may actually die, right? Depending on the circumstances, right? So this constant k, which essentially describes the happiness of the bacteria, right? I mean, the larger k, the faster they grow, right? So this constant k depends on a lot of things. It depends on them being in the right environment. In particular, constant k should depend on how much food they have, right? So let's suppose that k depends on this variable food, which is how much food is available in the bottle. So food restrictions. Okay. So now let's suppose that k is dependent on a constant c, on a variable c. So this constant k is not constant anymore. It's a function of food availability. Okay, and we're going to make an assumption about the food. How do you think that the food is consumed? So C of t is the food concentration. Does anybody want to suggest an equation for C over time? So as a first approximation, we're going to start with a bottle of food. We throw in the food in the beginning. We're not throwing any more food afterwards. And the food is, the bacteria consume the food. They probably poop the food in some way. We're not going to worry about how the food is destroyed, but the bacteria consume the food, right? So what would be an equation for the rate of food destruction? What do you think? So let's see. If there's no bacteria, then the food is constant, right? Okay. Now, the more bacteria there are, the faster the food is consumed, right? You would think, right? So then what?
Decreasing function slow at the beginning and then
Decreasing exponential function.
Decreasing exponential function. You mean like
Negative.
minus c?
No, that wouldn't be like negative e to the RT or something like that. Negative exponential.
the negative number because it would go faster.
Oh,
Well, but if you write something like this, whether we do it as an exponential or not, it's not going to depend on the bacterial population, right? If n is 0, right, then c prime should be equal to 0. So there better be an n in here. Okay, so then what do you think? negative n, for example, right? Okay, but there's probably going to have to be some constant in here. What do you think? Let's write it like this, minus alpha times n. What does alpha mean? Well, actually, no, I'm sorry, no. It's not really n, it's actually the rate of change of n. It's not the present bacteria that consume the food, but it's actually the rate of growth of the bacteria that are causing the consumption of food. So let's do it like this. Yeah. Actually, you can also assume the other one. You can also assume that if bacteria need food to just be there and survive and just hang around, then there's going to be an n term in here. But let's suppose that bacteria only need food to the extent that they're growing, right? So if there's for example 5 new bacteria, then there's going to be a consumption of food. If there's 10 new bacteria, there's going to be twice as much consumption of food. Okay, so then alpha will be what? Alpha is a constant that tells us how much food a new bacterium is consuming, right? The larger alpha, the more food each bacterium is consuming, right? Constant describing consumption of food by each bacterium, by each new bacterium. Okay, but we know that we know that M prime has that formula over there. So then C prime is equal to minus alpha times K of C times n. Okay? All right. Now, let's make a new assumption just to be able to analyze this thing. And let's suppose that K is proportional to C. In other words, the more food the bacteria has, the happier it is. Okay? We don't have to assume that. We can make another assumption. It's just that to analyze the system is going to be easier if we make an assumption about the form of this equation. Oh, Jesus. Okay, let me delete this here. All right. So now assume a form for the K of C. We're going to assume that K of C is equal to a constant times C. And here it's a little bit awkward to write on the board, but I really should follow the notation of the book so that we can read the book and follow the class at the same time. And the book uses this smaller case K. It's more of a kappa actually. This is a kappa and this is a capital K. Okay, and they look almost the same. But I mean, I'm not sure if maybe I should use a different constant for the board, but I think it should be fine. Let's just remember this is little k and this is large K. Okay, I think it should be fine because we're going to multiply by C. You can see the small k and the large C, so it should be okay. All right. So now this, how would you describe this assumption? What are we assuming here? So if there's no food, how fast do the bacteria grow? They don't grow at all, right? Okay. If there's a lot of food, then bacteria grow very, very fast, right? Now, what do you think? Is this a reasonable assumption to make, or does it have a problem? What if there's like 1,000 times more food? Is it reasonable?
The bacteria can only consume the food so fast.
Exactly. Exactly. If you remember, K is the proportionality rate for the growth of bacteria, right? The larger K, not little kappa, but large K, right? The larger K, the faster they grow. But bacteria, I mean, we know this about bacteria. If you give them as much food as they want, at some point, they're not going to grow faster than a certain rate. Because there's other things that they need. They need to be able to grow. They need to be able to turn this food into proteins and amino acids and whatnot. And they also need other sources from the environment. They need, they really need more time, They cannot grow arbitrarily fast. So really, K is what we call a saturating function. In other words, if C is really, 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 really large, K should not be arbitrarily large, but it should reach some kind of saturation and not grow beyond that, right? But for the purposes of the analysis, I believe we're going to actually solve the system, not today, but later in a few lectures, or maybe even on Wednesday. For the purposes of this analysis, we're going to make a simple assumption that the more food there is available, the faster the bacteria grow. Okay. So, all right. So now the ODE now looks like this. N prime of T is equal to K of C times N. And if you remember, now we're using this formula that it is little k times C, this kappa times C times N. Okay? And C prime of T is equal to minus alpha times K of Cn is equal to minus alpha times kappa times C times N. All right. Now notice that on the left-hand side, are the rates of change. For the two variables of the system, C and N. Okay? And on the right-hand side, we have functions of C and N. Okay? What this means is that if we know the concentration of food and if we know the population of N at any given time, then we can calculate the rate of change of the food and the population. That is the key idea of dynamical systems. That's the basic situation for a continuous time dynamical system, is that if you know the state, in this case food and population, you know the rate of change. Okay? That's it. So this is an example of a dynamical system, in this case a coupled system of two different equations. And mathematically now we can use mathematical tools to figure out how this thing behaves over time. All right? So, do you guys have any questions? Yes, sir.
When we're trying to model like any given phenomenon, how do we know like when to make assumptions and how to make reasonable assumptions?
Okay, that's a very good question. When we are working on a mathematical model, how do we know when to make assumptions and when these assumptions are reasonable? Okay? And it really is a bit of an art. For example, right here we made we made an assumption about this function. We assumed that it depends on the amount of food. That's because we wanted to throw in food into the system. We wanted to say, the amount of sugar really makes a difference. Let's throw sugar into the system and see how it behaves, how the whole thing behaves with sugar. And the way to include sugar into the system in this case is, let's say that the bacteria are happier the more food they have, right? So that's how you made this assumption about K being a function of C. Then you have to figure out what kind of function of C. Depending on what function of C you choose, you're going to get a more or less complicated system here. So if you choose a more complicated formula for K of C, you're going to have a more realistic system, but on the other hand, you're going to have a more difficult system to analyze. And this is really the modeler's problem. The modeler's art is, on the one hand side, you want to be as precise as possible. On the other hand, if you make it too messy and too precise, you're not going to be able to analyze it because it's going to be too difficult to solve mathematically. First of all. Second, you have more and more parameters. These parameters are going to influence the system. Depending on the value of the parameter, you're going to get one behavior or a different behavior. And bottom line is we don't really know those parameters. You can talk with a biologist to figure out the parameter values. And sometimes you're going to be able to derive those parameter values from experimental data. But the fewer parameters you have, the better off you are. Okay? Somebody also said about modeling that if they're given enough parameters, like 100 parameters, they can fit an elephant. You know, they can fit anything you give them, they can fit. And so this idea that you can cheat with parameters. The more parameters you throw in, the more chances you have to fit things however you want, and then you can choose parameters to do whatever you want to do. But you're still not doing anything particularly useful necessarily, right? So we want to keep it as simple as possible so that we can analyze it, and we're not cheating with parameters. But on the other hand, we want to include the interesting biology. Okay? And in terms of mathematical biology, which is different from other types of modeling, if you're modeling physics or if you're modeling engineering problems, if you're modeling the flow of air through an airplane, right? Or if you're modeling how a ball is thrown, you can always make simplifying assumptions, and you can find an environment where the assumptions are broadly satisfied. For example, if you don't want to use, if you want to throw a ball and you don't want to take into account friction with the air, you can throw the ball in vacuum. I mean, it's hard, right? But you can. You could do that. And you can verify this assumption of what happens if you throw the ball in vacuum. Does it really satisfy with what you want? But you cannot just assume that a bacterium doesn't need sugar, right? Or you cannot change something. Nowadays, sometimes you can, but generally you cannot change the biological system to satisfy your simplifying assumption, right? So the problem with biology is that it's very, very messy. And you have to deal with that messiness, if you will, right? So that's why modeling in biology is a little bit different from other types of modeling. Okay, any other questions? Okay, all right, so we're running out of time, so next time we're going to continue with this system, we're going to solve it, and we're going to make it a little bit more complicated, and we're going to start talking about units more. Okay, so great, thanks.